Hello everyone, and welcome to today's webinar in the SERDP and ESTCP webinar series. My name is Rula Adib. I'm a Senior Principal at Geosyntac Consultants in Oakland, California, and a coordinator of the webinar series on behalf of SERDP and ESTCP. I will be facilitating today's call. The webinar will consist of a brief overview of SERDP and ESTCP by Dr. Andrea Leeson, followed by a list of upcoming webinars in this series. After Andrea's opening remarks, we will transition to the technical portion of the webinar. Today's event features 3 PFAS presentations. First, we are honored to start with Dr. Stephen TerMaath from the Air Force Civil Engineering Center, who will provide a DoD perspective on the PFAS problem, followed by a brief Q&A session. Second, Dr. Jennifer Field will talk about characterizing fluorochemicals in AFFF contaminated groundwater at military sites. Her presentation will be followed by a second Q&A session. We will conclude with Dr. Chris Higgins, who will discuss the transport of perfluorochemicals in groundwater at AFFF impacted sites, followed by an interactive Q&A session involving our 3 speakers. With that, I would like to introduce Dr. Andrea Leeson, who is the Deputy Director of SERDP and ESTCP, as well as the Program Manager for Environmental Restoration. Andrea has been with SERDP and ESTCP since 2001, and before that she was a research scientist at Battelle Memorial Institute, where she conducted research on in situ bioremediation. Please go ahead, Andrea.
Thank you, Rula. And I'm happy to welcome everyone to SERDP and ESTCP's webinar today. SERDP is the Strategic Environmental Research and Development Program and was established in 1991 by Congress as a partnership between the DoD, the Department of Energy, and the EPA. SERDP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. SERDP funds both fundamental research as well as advanced technology development that ultimately impacts real-world environmental management. ESTCP is the Environmental Security Technology Certification Program in which we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under SERDP or other research programs and are designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. SERDP and ESTCP are complementary programs with much of SERDP research occurring at the lab and pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts are conducted. There are 4 program areas in SERDP, 5 in ESTCP. The Energy and Water Program area is only in ESTCP, while the other 4, Environmental Restoration, Munitions Response, Resource Conservation and Climate Change, and Weapons System and Platforms, are SERDP and ESTCP programs managed jointly by a designated program manager. Our webinar today is focusing on research and demonstrations that were conducted under the Environmental Restoration Program area. Environmental restoration has essentially 5 main areas of research: contaminated groundwater, contaminants on DoD testing and training ranges, contaminated sediments, wastewater treatment, and risk assessment. Our webinar series will be highlighting research and demonstration efforts from each of these 5 program areas. As you can see, our webinars will cover a broad range of topics, with upcoming topics covering chromate and hazardous material-free coating systems, to insensitive munitions, to long-term monitoring issues. The next webinar based on research and demonstrations under environmental restoration will be on March 10th and will focus on recent SERDP efforts on fate, transport, and effects of insensitive munitions. You can find more information about upcoming webinars on the SERDP and ESTCP website. Registration is now live for the next webinar that will be on chromate and hazardous material-free coating systems. I hope you enjoy the webinar today. Rula?
Thank you, Andrea. And it is now my pleasure to introduce Dr. Stephen TerMaath, who is the Chief of the BRAC Program Management Division at AFCAC in San Antonio, Texas. Dr. TerMaath's division is responsible for executing the environmental programs and real and personal property disposal for the 40 U.S. Air Force bases being closed or realigned under the authority of the base closure and realignment legislation. Dr. TerMaath has extensive experience in managing and executing restoration programs, research and development, and finding solutions to unique and challenging environmental problems. He has over 35 years in the military, private sector, and civil service. And with that, I turn it over to you, Dr. TerMaath.
Okay, well, thank you very much. I'm just going to kind of cover some broad and general aspects that we have. And first of all, I guess, you know, we've got the wonderful PFAS and PFOA, the perfluorooctanic acid and the perfluoric octanic sulfanic acid, the PFAS and PFOA. But the Air Force first began using aqueous film-forming foam back in 1970 that was about 6% active ingredient, being water and then 6% active ingredient. The active ingredients were the PFAS, the PFOAs, and a few stabilizers in there that were purchased. And it was found to be an extremely effective, and there's been nothing better since then to put out petroleum fires, particularly associated with aircraft fires. And when you look at how we operate an Air Force installation, and now that we've transitioning out of the AFFF, we're in the process of replacing all those AFFF with a PFAS and PFOA in them. You look back and say, well, where have we used it historically? And there's literally hundreds of potential release sites. And in the BRAC program at those 40 installations, of which only about 30 or so, less than 30, had flight lines and other activities that would have had the AFFF, we're still looking at having to go back with a potential of between 350 and 400 sites on the combination of those bases. So we end up with 10 to 15 sites that may have had AFFF usage on installation. On the next slide, we talk about, okay, now we have all these sites, we've got these potential release sites and everything. What does that mean? Well, first of all, as a regulated group, we look at the provisional health advisories used as the allowable levels in drinking water. And that's the primary driver right now for the response activities that we're doing on the AFFF to locate and find those. And we initiate a program to, as I said, identify all those 350 to 400 sites that may have had a release. And in addition, it's been interesting since there are some communities now that under the UCMR3, they are going through and requiring analysis of public water systems. So far, however, the one place where, or the locations that we've had impacting that is sometimes we find it before the UCMR3 sampling is done. So it's a combination of that plus the activities the Air Force are doing that are locating what we hope will be few and far between impacts on a public water supply, but they may occur. Okay, what's our approach? Well, coming back to release sites, well, what kind of sites do we have? We have places where we fought a fire. We have fire training areas where they practice putting out a fire. We have the actual called dispensing equipment, trucks and other things that were used to dispense it. They would periodically test that equipment to see if, one, it was mixing it properly and applying it properly over their expectations. One additional site that's not mentioned here is what we call hangar deluge systems. And those systems were in a hangar where there was a high risk of a fire because of fully fueled aircraft or something that might have been associated there in an alert fashion. They had the deluge systems in there. And like any good system, it went off on its own sometimes, thinking that it had detected something when there wasn't. And so you would have that come off. Now, how kind of volumes are we talking about here? When we fight a petroleum fire, you're talking about right now, what we've been able to talk through with our fire department folks and everything is that if there was a fire fought, there was an average of 90,000 gallons typically used with a 6% solution. Because what you have is when you have the truck with the nozzle mounted trucks come up, they're dispensing at about 1,000 gallons a minute. And frequently on fires you'll have 3 trucks responding to that fire on an aircraft. So, and then after the trucks get the bulk of it out, you're still going home with handheld hoses and everything. So that's how you end up with fighting one of those fires to completely extinguish. You're anywhere from 30 minutes to an hour after the response to get that flame out and a safe egress that they can go in. So that's one thing that you have. So you can have some very high things there. And fire training areas, before they lined them and everything, they would you could have AFFF applied and leak into the and go down through the ground into the groundwater. But typically a fire training area also had petroleum products associated with it. So one of those areas we've done a lot of studies on and done cleanup on that to remove the petroleum products that may have gotten into the groundwater. But now we may have the AFFF from those locations. And the others, locations that we talked about with dispensing calibration, they did those frequently, far more frequently than they did training and everything. So those are often, at some bases they did in the same spot all the time. Other bases they went around and did it in different places on the base. So it just depends on where it is, where that contamination may have escaped and gone into the groundwater. The good news is that over the years there's been a lot of hydrogeologic information accumulated at our installations because of other issues that we've done under the restoration program. So right away you have the potential for the releases. We've got good knowledge of the hydrology to make some assessments initially. And so now we look at pathways. What is the pathway that may be there between that release and a receptor, meaning a private water well or a municipal water well? So that's where we're focused very much on in doing that. Next slide. So if we look at that, our immediate focus is protecting the public health, protecting from those water supplies, and take the immediate action to mitigate wherever we found those on there. So far in the BRAC program, we've only had one public water supply impacted, and when we look at the bases right now, we've probably got a handful of private wells that are in the BRAC program. Now there have been some active duty installations that have higher numbers on that with that. But again, that all comes by with what's adjacent to the base, how many homes are there, and are they on municipal or public. But again, we focus on those. And the mitigations that we do there is normally we take the samples out there, we get the homeowner's permission to take those samples. And so if we ever had a number come up above the the provisional health advisory, you take immediate action for normally within 24 hours we're providing bottled water or other things until we can get a better solution in there. If it's a well, we tend to, within a very short period of time, we'll have a granular activated carbon system installed on their well system. With the long-term solution, that if they're near a municipal supply, we will hook them up to a municipal water connection for the long term. So that's where we kind of are on there, again focusing and principally focusing on the protection of the public when we look at that and the water supplies. In doing this so far, we've had a few observations from the limited amount of data that we have with regard to, trying to look at configurations and everything else. But the PFAS and PFOA seem to move slowly through the groundwater. We'll look at some places, and if you're at a distance of about 3/4 of a mile, in some locations we're finding that they're down below the PHA. In other places it's at least an order of magnitude below where it was at the release site. In any case, by the time you get to a mile or a mile and a half, we're talking about being near the detection levels. And again, those are general, limited information that we have right now, but those are the kinds of things we're seeing. So given that some of these releases started back in 1970, we're talking about a fairly slow movement. And even if we take the worst case scenario that I was on the mile to mile and a half means, that assumes that the release was yesterday in, say, 1990 and released, even though that site may have had 20 years more of experience. But the last time we used the site was a certain date and had that. That's how we collected that. So, and the other thing, I talked about the petroleum contamination that was at a fire training area. The PFAS and PFOS are more expansive. In other words, they're many times larger, the plume, than the petroleum plumes that we had identified on there. Okay, so now we've got all that. We're moving out. We're trying to do that. But obviously already early in the program, we're seeing, you know, what are the alternatives to granular activated carbon? We know that there's resin technologies out there that we've got to get proven out, and we'll see what happens over time on that. And the alternatives for groundwater restoration, I think you'll hear a little bit about that mentioned today. But when you talk about, you know, does it degrade? Does it, you know, chemical degradation on its own? We have biological degradation. Is it going to be like TCE that started out with the only systems at that time for actually treating it were granular activated carbon, or you stripped it out and put it into the air. Then over time found out that there were other mechanisms that can be applied, and today it's the other mechanisms that have far taken over and are very effective. So fate and transport, just like we talk about, where does it move, how fast does it move, what happens to it in the groundwater regime. And then the other big thing out there is, okay, we've got PHAs on there, the health advisories and everything. Unlike, you know, past emerging contaminants that I think there was a consensus on the human health effects, I think there was a faster agreement on what the levels needed to be, whether it was the groundwater or wherever on there. But the health effects knowledge and everything, I think, has created a little different and a little more uncertainty about where we're going with levels and restoration requirements and everything else. And I think that's probably from a public perception, where are you these days? Okay. So that kind of concludes my what I was going to say. And I think, Rula, you said there would be some questions at this point, or we save them for later?
Actually, we received quite a lot of questions, so
okay.
we'll take a few minutes and see how far we can go, and whatever we don't answer during this Q&A session, we'll leave towards the end. Can you please start off by telling us when you think you will have an understanding of the scope of the PFAS issues facing the Air Force?
Yeah, like I said, we're doing the equivalent of preliminary assessment, site inspection on those, and some 300 and some odd of the Air Force sites, closer to 450 or so, will probably be completed in the next year and a half, and I say over the next 2 to 3 years, we hope to have overall in the Air Force the PASI activities to where we'll know where our sources are.
Great, thank you. Can you tell us if the Air Force is planning to move to a gaseous extinction agent if they are eliminating AFFF from their systems?
You know, the MIL spec on that is being looked at, and I think you'll still be looking at another primarily liquid type dispensing things and to replace the PFAS and PFOA.
Great, thank you. A question about the uses and sources. Was AFFF applied to runways in case of emergency landings?
It had been used sometimes for that, but in general, that's what I was talking about. When you fight a fire and everything, there was lots of techniques that have applied over time. One of them they did did try to apply to a runway when there's a landing gear problem and other, but that I don't think that had extremely widespread usage. Again, it was for selected scenarios.
Thank you. Does the Air Force have a strategy for evaluating other perfluorochemicals beyond PFAS and PFOA? What about the other compounds that are present in AFFF that might be of concern?
Well, certainly in that case, I think in the past webinar you heard from Paul Yaroshak that talked about the Department of Defense emerging contaminants listing. And as those come up of interest in the environmental community or EPA starts looking at those, we then take on and look at those based upon those activities, because we don't have an independent thing that's looking at health effects on that. We rely on the regulatory community to provide us that information, and also people like CDC, ATSDR, and others that are in that business.
Thank you. There are two questions from Atlanta International Airport with respect to overall concerns associated with PFAS contamination. The first question is, our training facility is adjacent to a surface water and a river. Is the Air Force concerned with water supply wells, or are surface waters of concern, or are you just focusing on groundwater and soil contamination for now?
We are primarily focused on the groundwater. However, if there were discharges or something in the surface water and there was nearby intakes or whatever, and we saw something, obviously we would follow that pathway.
Great, thank you. And along the same lines, the training facility at this airport has discharge water that is contaminated with PFAS, and they have a permit whereby they are discharging the spent fluid after recycling it for multiple uses to the city's sanitary sewer system. Is that something that the Air Force is dealing with, or again, right now the primary focus is soil and groundwater contamination?
I think there were two issues involved there. The one is if they're doing a discharge to the wastewater treatment plant, what we've seen is there is no reduction, or there is a reduction because some of it gets tied up in the sludge, but in general there's no real treatment as it passes through a wastewater treatment system. We haven't studied that a lot, but the observations we have now are that it doesn't get treated. So that is another avenue to look at, because I think that's where their question is generated. Did that answer the question?
Yes, sir. Thank you.
Okay.
And one last question. There's 19 more for your 10-minute quiz and presentation. So is the Air Force doing public outreach to former active duty and civil service at sites where it has been demonstrated that wells were contaminated with perfluorinated compounds?
It will depend on, frankly, how we get towards those regulatory levels and more information on that. We have at the one location where we had a municipal water supply, we have sent letters to notify them that they have been exposed. And that was based upon people that were assigned to the installation, and both military and the civilians that were assigned to the installation with regard to that, because we have no way of knowing the total population or anything that's around, so we would rely on notices if a city or might went out. But I think the real problem right now is without the consensus on the health effects on there, it's hard to tell anybody anything other than the fact that they have been exposed.
Great, thank you. And before we move on to our next speaker, can you please say something about the AFCAC website that you have on perfluorinated compounds?
Yeah, we do have a website that is on that slide you're looking at there. That website is where we are putting up information, and probably there's some information on what all the Air Force is doing, but probably as much as anything there are links back to ATSDR and other places where they have more in-depth information on the health effects and some other things on there.
Great. Thank you very much for a very informative perspective and description of the problem facing the Air Force. And with that, I'd like to go ahead and move on to our second speaker today. The next presentation will be given by Dr. Jennifer Field, who is a professor with the Department of Environmental and Molecular Toxicology at Oregon State University. Jennifer's research focuses on the development of quantitative analytical methods for organic micropollutants in both natural and engineered systems. She is a pioneer in the area of fluorochemical occurrence and behavior and has focused on groundwater contaminated by firefighting foams, municipal wastewater treatment systems, and municipal landfill leachates. And with that, I turn it over to you, Jennifer.
Well, thank you very much, Rula. And we quickly want to move to the agenda for today's talk. I'm briefly going to touch on the unique chemistry of PFASs and then describe our SERDP's technical objectives, briefly the approach, and then move on to what the project is bringing to the topic of AFFF contamination at military sites. So I have a slide here, background, but it's really to remind everyone what makes these substances so unique. And you can see from these cartoon images of the chemicals that the carbon-fluorine bond is, there's several of them in the case of PFAS, which is up here in this cartoon positioned at the air-water interface. And you can see the large number of carbon-fluorine bonds along the backbone of PFOA. So what we know is that the carbon-fluorine bond is the shortest and strongest in nature. And when you assemble a number of these together, as in the case of PFAS and PFOA, what you have are really unique properties that were exploited in the commercial marketplace. And this is this general tendency to repel both oil and water compared to what we might think of as hydrocarbon behavior. So these characters have both hydrophobic and oleophobic nature. And it's also precisely why they do such a good job at the air-water interface in spreading water over burning fuel fires, which was the whole point and function of the aqueous film-forming foams. But keeping an eye on this general nature of the carbon-fluorine bond, the bottom line is there's very few engineered or natural degradation processes that can actually break down, specifically these two chemicals you see on the page. And so that means that these chemistries are excellent for being used in applications that are very aggressive environments, acidic, basic environment, oxidants, which of course you can see the problem might be when we try to develop oxidation remedial approaches. We really need strong ones in order to overcome this strong bond. And they're also stable in heat, which is why we can throw them on burning fuel fires. The net result, when we look out into the environment, it just simply takes too much energy to break these bonds when we're trying to degrade these materials either naturally or through engineered processes. And microorganisms simply cannot gain energy from breaking these particular bonds. And so we do have these unique properties. And then when we look forward, this is just a reminder that this topic, we're very focused today on AFFF and sites, but we do belong to a broader question and a broader issue, and this is PFASs around the world. There is an internationally accepted nomenclature, and nomenclature is very helpful here because we need to communicate not only inside and outside the DoD complex, but as the previous speaker mentioned, we have stakeholders, we have airports, and so it's really important that we speak the same language. And so the term PFCs is a term that we'd like to see sunsetted in the sense that PFC is a very restricted term. It does happen to be appropriate when we speak only in terms of PFAS and PFOA, because strictly speaking, perfluorinated means that those carbon backbones are fully fluorinated and no longer contain any hydrogens. But it's a restrictive term, and it turns out when it comes to AFFF sites, very few meet this restrictive term. So that's why we have to include the term polyfluorinated. And you see an example here. This chemical is also very important at these firefighting sites. And it turns out it's not necessarily in the original AFFF formulation, but it's present in groundwater. And here's an example where 2 of the carbons have hydrogens. And this is actually the signature or calling card of the alternative chemistry that was used to get around the original 3M patent. So it's an entirely different chemistry, has a different source. And the other important point is this linkage right here also represents a potential weakness in the molecule, making polyfluorinated, this one and other polyfluorinated substances susceptible to biodegradation. And so I'll touch on that a little bit earlier. So to be appropriate, when we talk very generally about the plethora of substances that exist at AFFF sites, PFASs is actually technically the more appropriate term. So this our SERDP project has been operating here for a few years. And when we came into being, the first question was, do we really understand what was applied to these AFFF sites? So the first objective was simply to characterize what's in those AFFFs. And I'll show you today how we've advanced that knowledge. The next was to turn our attention to actual groundwater sediment soil. And then, of course, to compare what was applied versus what do we see in this environmental media. Next is the role that Dr. Lisa Alvarez-Cohen down at UC Berkeley has played, and that is to get into the biodegradation of the, in this case, the antyl AFFF under aerobic and anaerobic conditions. And that's some exciting work that's being done and very pertinent to many, many sites. And then most recently tackling, characterizing the absorption of some of the more interesting PFASs that we now know occur at these sites. So having said that, the tools that we use are tools that you might expect. So mass spectrometry and oxidation-based assay are playing pivotal roles in the characterization. I do want to call out the oxidation-based assay was developed by Dr. David Sedlak and Erica Hautz at UC Berkeley. And I'll touch briefly on an alternative technique known as PIGGY, and that'll come up later. And that was to get after the characterization AFFFs and then environmental media. Dr. Alvarez-Cohen is using microcosm setups under aerobic and anaerobic conditions, and then of course the classic batch absorption experiments are used to characterize the transport potential of some of these new identified chemistries. Okay, so on to the AFFF characterization. When we look into a number of 3M AFFFs, and again, these were supplied by the Air Force Fire Chief. We were very fortunate to get 60 formulation across the wide complex, and we got a very interesting one not that long ago. And when we look at this variety of 3M AFFFs, we can of course confirm that PFAS was a major component of 3M AFFF. 70%, for example, by weight of the fluorinated mixture is PFAS. So that explains, of course, the high percentages of PFAS at many, many sites. But it's also important to note, and I think a question came up earlier, what about this C6-sulfonate? Well, it turns out in some of the AFFFs, C6-sulfonate actually can exceed that of PFAS. So there is no one particular composition that is going to be spot on in terms of this is what was applied to a site. So there's variation, and that actually makes sense. When we look at the complicated electrofluorination chemistry, what we see is that PFAS, first of all, is never alone. You see PFAS, you see a lot of its other brothers and sisters in the homolog family, and I'll touch on that earlier. But C6-sulfonate is always present at these sites as far as we look at it. It's interesting when it comes to PFOA. PFOA is a minor component of AFFF, 0.5%, for example. And so it's not clear yet that the PFOA we see in groundwater is actually derived from the formulation itself as an ingredient, but it may be what we're seeing as PFOA as a biodegradation product that has formed since the application of the AFFFs. I'll mention a little bit later that we now see and appreciate the fact that we have even shorter chain substances than originally believed. As I mentioned, the chemistry is a bit messy, and so the 3M AFFFs contain, when we think of just the sulfonate family, we have as short as C2 all the way up to C10. And we now also see cationic substances and zwitterionics. So for example, here's an example of a cationic substance in the 3M formulation, and isn't this in character here on the right an interesting one? 2 anionic sulfonate groups, 1 quaternary amine in the center of the chain. Here we have a quat and a sulfonate. So we've got some complexity here, and I'll talk briefly about what we need to know about these chemicals. When we look into the Telmer-based AFFFs, they're out there. These have different brand names: Ansel, National Foam, Fire Aid, Buckeye, for example. PFAS in U.S. mil-spec is not present in these telomere-based AFFFs. Now, I've heard folks from overseas say, well, we've seen AFFFs with PFAS in it with the telomeres. That may be the case. But when it comes to U.S. mil-spec, we do not see PFAS in the telomere-based. Where you might see this in other scenarios, perhaps in other AFFF markets that weren't U.S. mil-spec, is that formulators might have mixed two things together. But when it comes to the U.S., we see very distinct differences between telomere AFFF and PFAS-based AFFF. When we look at the telomere materials, you actually can see evidence of why we end up seeing high levels of telomere sulfonates in groundwater. It turns out the fluorotelomere sulfonates that can be up to milligram per liter levels really are only very trace components in the telomere AFFF, again signaling these may be biodegradation products. And also telomeres, they share that character with the 3M. It's a combination of anionic, cationic, and zwitterionic structures. When we took those new chemistries and put them together with the legacy carboxylates and sulfonates, we created an analytical method, and then from a voluntary basis, Air Force and naval bases volunteered select samples, groundwater samples from various sites. And we applied this methodology. And what you see here on this table is an example where, and again, it's just a subset of the data that's actually present at these sites. But let's look at the top of the table. This is actually the precursor chemical that exists in the Ansel formulation. We still see that at Site 1 and Site 2, there are up to microgram per liter levels of this material remaining in groundwater. But look at this. This telomere sulfonate is up in the several hundreds of micrograms per liter. This is completely flip-flop from the AFFF itself, suggesting this is an intermediate. It's metastable. It's certainly stable under the prevailing groundwater conditions of many sites. That's why you see those numbers. When you look farther down the list, here are the cast of characters people are increasingly familiar with, the sulfonate family. So, and it's not all of them. Here's the C4, the 5, the 6, the 7, and 8, and it goes up to 9 and 10 at these sites. What's interesting to point out is if you're a consumer of analytical information or you are asking for analyses, keep in mind that if you ask for the UCMR3 list, this is the EPA program that came up earlier, it's focused on drinking water, but it is also a suite of 6 analytes. You will get data for the red analytes, the C4, the 6, and the 8. But keep in mind, if you're at an AFFF site, there's also the C5 and the C7, and they will be invisible to that methodology. If you ask for the EPA method 537, again, established methodology, which was only originally designed for drinking water, you will not see the purple analytes here. So the point is we are seeing the major players when you ask either for the EPA method 537 or the UCMR3. For example, this site PFAS is hitting a milligram per liter. But there are other species, including very short chain ones, that may move more rapidly in the subsurface that are also present. And the issue of GAC for drinking water treatment came up earlier. These species, the C4 sulfonate and carboxylate, will present challenges. What we do see is when we look broadly across these sites is that the U.S. military groundwaters do hold the world record. We see up to a milligram per liter of PFAS. This is an individual species, PFOA. We've hit 6.6 milligrams per liter, and that fluorotelomere sulfonate, not to be outdone, has topped out at 14 milligrams per liter. So if we move on here, as mentioned a little bit earlier, the 3M chemistry is complicated, and it turns out it's a homologous series. And there's nothing magical about C4 being the bottom of the line. It turns out C2 and C3 sulfonates are present not only in the AFFF and independent of manufacturing date, we also see it in groundwater. So we see that if you, well, first of all, there are no health advisory limits for these two species. But if we look to the Minnesota guidelines for the C4, so the next one up in chain length, they've set a health risk limit of 7 microgram per liter. So what we see is C2, C3 exceeds those limits. They're also highly mobile in the subsurface. There was a question earlier about whether or not if you map your PFAS and PFOA, is that your plume? I would suggest perhaps not, because these chemistries may actually make up those leading plume edges. And then finally, as mentioned earlier, they may also be challenging to remove. Others have seen the C4 sulfonates are very challenging to remove. This is just going to compound that issue. let's see, moving on. Trying to wrap up the site characterization. So where are we now? Well, we are very fortunate to have Chris Higgins as our collaborator, and with his talented team, we are finding additional structures not only in AFFFs and groundwater. Why does this matter? This is what we want to do, is to stop the discovery and find out all the highly fluorinated substances. Why? Because they may serve as indicators of in situ biotransformation. For example, this one species here. It's an intermediate in biodegradation. It's stable under anaerobic conditions. It could oxidize to PFAS. These also become remedial targets. And once we finally understand not only frequency of occurrence and concentration, we can then begin to understand if we should prioritize these with regard to estimating risk. All told, when we look at the complex chemistry, this is why it matters. They all share properties of high aqueous solubility and low vapor pressure. As Dr. TerMaath mentioned earlier, they cannot be removed by air sparging, and in fact they become relatively enriched in the aqueous phase. You have to be careful where you discharge, dump, or treat that. We also know that some of these more interesting structures, anions, zwitterions, they may have different transport potential than cation. I'll mention that here in a moment. Relatively little is known about biodegradation. I will mention some of the data on the Ansel materials that have been looked at down at UC Berkeley. And what we see from a tox point of view, when it comes to humans, again, we have more human populations that have been affected, and this will help guide and create a consensus. Relatively speaking, there's less ecotox data, and this is one of the reasons why SERDP has recently funded a series of grants trying to understand the ecotox. They saw the data gap, and they're attempting to fill it. And when it comes to the zwitterions and cations, very little is known. However, what we know from looking at hydrocarbons, when they're cationic, they tend to disrupt membranes in aquatic organisms. So that generality probably holds true here as well. And the last bit on site characterization, there are these new two tools for trying to understand the total fluorine. Simply until we can capture all the individual species by LCMS. The TOP assay, it's now a published method for quantifying precursors by watching the oxidation of the polyfluorinated substances to carboxylates and measuring the net increase when we expose a sample to oxidation. Elegant, simple, provides a measure of total fluorine. Another one, promising technique, total fluorine by PIGGY. It's a spectroscopic method. Groundwater gets sorbed onto media, bombarded with protons, and what we have is a very characteristic signal, 2 peaks for fluorine. And it promises to be a high throughput, quantitative, and inexpensive screening tool, which is something that's really needed in the arsenal of Analytical when it comes to these sites. ESTCP has funded a recent piece with Navy partners, and the aim is to finally close that mass balance, to put these tools together for analytical characterization and total fluorine to differentiate sources on site. As mentioned earlier, we have AFFF that's being used in a number of sites, but landfills are a point source. Wastewater treatment plants are a point source, and of course we have atmospheric deposition that can impact sites. We want to put these tools together to differentiate sources, to develop conceptual site models with the goal of understanding human and wildlife exposure, and to assist in creating remedial treatments that capture all the relevant species. And then with all of this, hopefully we can identify those final data gaps that remain on transport, biodegradation, and toxicity. So just a note here on biotransformation. This work came out in Environmental Science and Technology this past year. This was the work by Dr. Lisa Alvarez-Cohen and Katie Harding, where they looked at the Ansel precursor and they watched its oxidation in aerobic systems to a more highly oxygenated species, ultimately to the fluorotelomere sulfonate, thus explaining the potential high levels of these chemicals observed in groundwater that are also stable under prevailing groundwater conditions, and ultimately the formation of shorter chain dead-end carboxylates that we also see in groundwaters. The anaerobic work that was conducted under nitrate, sulfate, and methanogenic conditions is forthcoming, and that will be an exciting addition here in this next year. With regard to sorption, what we know is there was a data gap on the transport of the telomere sulfonates. What we see is it's more mobile than PFAS. When we look at results from batch sorption experiments, when we look at zwitterionic compounds, we see that they absorb less than their anionic compound. So despite the increased molecular weight, we see the increased potential for transport because of this polar functionality, particularly that end capping here with the anionic group. Conversely, and in contrast, cations absorb very strongly. And the hypothesis is developing is that we may have immobile source zones in the sediment that where the cationic material has sat tight over the years. And so that's an important development. And of course, if you look at these structures, you see that they are going to be susceptible to impacts in pH. That carboxyl group here in the middle and that cation down there at the bottom. So pH is going to have a role. So in conclusion, I'd like to state that PFAS and PFOA are important. And as many of the military branches have stated, if you see these, basically it's the tip of the iceberg. You know that others are out there. And so it is important to note that they're not the only major PFASs out there, but they are the ones that we have the provisionary health advisory values for. It is important to state that the telomere-based substances do biodegrade, but those intermediates appear to be metastable in groundwater, and they thus become remedial targets. The telomere substances do not degrade to PFAS. That's just not chemically possible. And that's a clarification of that. The mobility in groundwater, anions are going to outpace Zwitter ions. Zwitter ions right now are unaccounted for, and then the cations show very limited mobility. When it comes to mobility, anions depend on chain length. That was demonstrated by earlier work in Chris Higgins, and we're just adding to that, and he'll talk more about that here in just a moment. And what we see is that the mobility of many of these substances are going to be influenced by sediment, soil, and water geochemistry. So the SERDP program has brought tools to the bear here that we can help create more accurate conceptual site models. We want to help fully identify all the remedial targets and thus help in the selection of approaches that ultimately decrease the time and cost to treating sediment, groundwater, soil. We want to inform optimized monitoring for capturing the species that are important for decision making, for fingerprinting, including source zone identification, because we need accurate predictions of transport. And then, of course, finding indicators of in situ biotransformation may help us understand and manage those processes and enhance those processes. And lastly, as mentioned earlier, groundwater is a potential source for drinking water on base and off base. And we really have to bring some attention to the short-chain PFASs due to their mobility and challenge when it comes to removing them from groundwater. And with that, I would like to conclude and acknowledge my co-authors. Thank you.
Thank you, Jennifer, for a great presentation. I would like to remind our audience to submit questions by using the chat box on the left-hand portion of the screen. We have received a number of questions for you, and I'm going to pose them to you, Jennifer. Can you please start off by telling us whether telomere-based AFFF are safer to use than the PFAS-based AFFF, and are they as effective for firefighting activities?
Well, the first question is safe, and there is no simple answer. I know that the telomere products have been described as not having PFAS, and that is true. But this note about the biodegradation, as you saw earlier in the pathway, the telomere-based materials can biodegrade to metastable intermediates, including the short-chain carboxylates, which are found in humans as well. So the actual answer to that I have to leave to risk assessment. I think it's a matter of making choices. And so we provided the information for people to make that choice. So it's not a simple choice. PFAS is listed on the Stockholm Convention. PFOA, not yet, but I believe it has been proposed. And our EU colleagues can probably speak to that more directly. In terms of effectiveness, they all meet mil-spec. Okay, so there's a very intensive program by the Navy. It was originally and still conducted by the Navy, and they are the group that ensures that formulations meet mil-spec. So in terms of providing the function and the performance, that has been established and documented.
Thank you, Jennifer. Can you tell us what the analytical method for fluorotelomers is?
Yes, that was published by my student, very talented man, William Bakke, who now works for the state of Minnesota. So it's in Bakke, B-A-K-E et al. It's an environmental science and technology manuscript, and we're happy to share that. Please just contact me by email. So it is published methodology.
It is, okay. Is it commercially available? Can people go to a lab and request analysis for fluorotelomers?
There are laboratories that can do the telomere sulfonate. Yes, there are, but very select ones. The Bakke method is much broader spectrum, but yes, the telomere sulfonate is now emerging into the U.S. commercial market, and you can see that. I believe Test America is an example. Access in Canada offers this, so that is available.
Thank you, Jennifer. You mentioned the problem with GAC getting the C2 to C4 sulfonates out. What is known about the toxicology of the ultra-short carbon chain sulfonates? Are there any studies out there?
On the C2-3, none that we know of. There is, I would say, by comparison to the C8 chain length, PFAS, there's relatively less about the C6 and below. But there's definitely a focus there because we do see that they are making it that humans are exposed to these. We have them in our blood. We have them also been shown to be in breast milk. So they are relevant substances, but I would say there's vanishingly less in the literature on the toxicology of these substances.
Thank you, Jennifer. If we do not see PFOA and PFAS in soil and groundwater, can we conclude that the site has not been significantly impacted? This is a question from the California DTSC.
I would say, based on our experience and what I've heard of others, is it's a pretty good bet. I wouldn't be 100%, but I would say when it comes to AFFF, if that's your source, if you don't see PFAS and PFOA, there's a pretty good bet. But I'd be also scooping up that telomere sulfonate if I could, just to mix that off, because they have different origins. So cautious, possibly, yes. How's that for hedging?
Good hedging. Thank you. Can carbon fluorine bonds be broken under anoxic conditions?
Good question. I think that's a wonderful question, and a lot of people want to know the answer to that. And that may be one of those focus areas where some of the SERDP-funded projects may show some progress. So there's some talented people working on that question. That's not my area of expertise, but I think we can look to the SERDP program to possibly be funding work along those lines.
Wonderful, thank you. Maybe time for a couple more questions. I'm going to ask this question because it's coming all the way from Sydney, Australia, and it's very early in the morning over there. Can you please tell us how branched isomers for PFAS, PFHXS, and PFHXA are quantified?
Well, let's consider that we have a broad audience, not all of which are dyed-in-the-wool analytical chemists like myself and the questioner. Let's step back and take the question. It depends on the analytical lab. PFAS, by its very nature, is branched and linear, and so the questioner knows that. So when you look in groundwater, sediment, and soil, so not biological systems, we always see the branched and linear. So you need to include that branched portion of the signal. That's part of PFAS. So if for some reason someone is ignoring that, your numbers are going to run low, your concentrations are going to run low by 25%. So if you're using a lab, the current state-of-the-art, you should be getting it could either be separate or some, doesn't matter, but include those branched because that's part of your total concentration. And that's true for all of the sulfonates. We just happen to have standards for the C6 sulfonate, which is branched, but they're all branched and linear. It's an inherent stamp of the chemistry. And so that's an important question, and if you are a site manager and for some reason your lab has not been including the branch and then they do in the future, your numbers could jump up. So that's just a note that it's an important topic. But going into the actual quantification here, I think is probably too much for the general audience, but it's an important topic. I would like to applaud the question.
Thank you. And just one final question. I want you to think about it both ways. The question reads as follows. Is it enough to monitor groundwater for PFAS and PFOA and the other PFASs that are listed under the EPA-approved method 537? You already mentioned that if you look for PFAS and PFOA and you don't find them, it's not very critical to go back and look for the other PFASs. But if you do find PFAS and PFOA, is EPA method 537 enough, or should we be caring about each and every fluorinated chemical that might be in groundwater given your groundbreaking work?
Well, Rula, that's a nice simple question to end on. Okay, so there were a lot of pieces to that. Let's say you have a longer plume and you're fairly downgraded. You don't see PFAS and PFOA. That does not mean you may not have some of the shorter chain material. So it's important to look at what you're trying to do in the context, let's say, of a groundwater flow transect. So you have to be cautious there. But let's say if you're near a hypothetical source zone, you thought stuff was AFFF was used, you don't see PFAS and PFOA. Well, that's pretty interesting. You may not have. Well, first of all, I've not heard of a site where AFFF has been applied and you don't see these substances. That doesn't really occur. I did see a question roll by though. Is it used in forest fires? Not to my knowledge. It's too expensive. It's not designed for that type of class of fire. So ideally it should not be used. Forest fires or burning wood. It's really a special application and should be confined to that. So I don't know if that answered your question, Rula. I think there's some nuances there, and I'm somewhat loath to just make it black and white. You have to really look at the information in context, and also what kind of decisions are you trying to make. Is it drinking water source protection? That might require a little more scrutiny than, say, a different kind of concern.
Great. Thank you, Jennifer, for trying so hard to answer the question so beautifully, but we are out of time, and I'd like to transition to our last presentation today, which will be given by Dr. Chris Higgins. Chris is an environmental chemist examining the fate and transport of environmental contaminants in both aquatic and terrestrial systems. In particular, he studies chemical fate and transport in these systems, as well as the bioaccumulation potential in plants and animals. Contaminants under study in his laboratory include poly and perfluoroalkyl substances, which we've been hearing about today, in addition to other contaminants of interest. And with that, I'd like to turn it over to you, Chris.
Great. Thank you, Rula, for that introduction. And it's been a real pleasure listening in to all the great questions that have been coming in from the audience. And I'm really pleased to be here speaking with Jennifer and Dr. TerMaath on this topic. Just to kind of jump into what we're going to be talking about, I won't go too much into detail in terms of the agenda, but really I'm going to try to give you a sense of the motivation for the work that we were doing or have been doing as funded by SERDP, a little bit on the way we did the work, and then really focus in on the results that we obtained from this work. So the motivation for this is that, as indicated from our previous speakers, these perfluoroalkyl acids, and I'm going to use that term as a subset of the poly and perfluoroalkyl compounds or substances. So these are the truly perfluorinated species. These PFAS, we know they're in groundwater, we know they're transported in groundwater, and shown here on the left is actually some work that Jennifer Field had published a number of years ago. And then on the right is some more recent work that we had done at Ellsworth Air Force Base, looking at the presence of these compounds in groundwater plumes as well as soils. And that was work that was again funded by the Air Force. And as you can see, there's some spatial distribution to these plumes, and there's maybe potentially a difference in terms of the spatial distribution of these two different compounds, shown hexanoic acid and the octanoic acid up here on the right. However, when we started this work as funded by SERDP, we had some transport information for some compounds, but fundamental transport parameters were generally lacking for the much broader suite of perfluorinated species, particularly the perfluoroalkyl acids, than were needed to really assess these sites. So that was kind of the motivation for our work. The other thing I'll mention here is, as Dr. TerMaath mentioned, when these sites, at least at the fire training areas, these sites had not just HFF applied, but then often their fuel had been lit on fire essentially for their fire training exercises, and so there were hydrocarbon plumes at these sites, and possibly in some cases naphtha and chlorinated solvents as well. And some of those co-contaminants and or co-contaminant remediation strategies that might have been employed at the sites might have affected the transport of these compounds. And so we really wanted to look at that. So the objectives and the questions that we're really trying to address here in this work are, what are the effects of having those co-contaminants present on the transport of these perfluoroalkyl acids? Essentially, how are they transported with and without those co-contaminants? How do other biogeochemical conditions affect PFAA transport? And I'll just note, I saw a question earlier about pH effects on transport. That was known before we started this work, that the pH of the system will affect the absorption and hence the transport of some of these compounds. But then the final question, we really wanted to delve into if the co-contaminants are undergoing some sort of remediation, and we focused primarily on chemical oxidation, in situ chemical oxidation, to what extent were those technologies and those co-contaminant remediation approaches affecting the perfluoroalkyl acid fate and transport in the subsurface? So the initial conceptual model that we started with was these compounds were being released as part of HFF release, possibly with the presence of fuel, and which might form naphthals or non-aqueous phase liquids in the subsurface. And the perfluoroalkyl acids might be interacting with lots of different things. They might be interacting with the solid phase, both the mineral and potentially organic matter in that solid phase. They're certainly going to be affected by the solution chemistry, which I alluded to and can touch on a little bit more. But we didn't really know to what extent they might be interacting with, say, the non-aqueous phase liquids present at these sites, nor to what extent any sort of remediation that might be going on or have happened at the site, to what extent that might have affected the transport of these compounds. And so we really wanted to understand and explore this conceptual model through our work. The approach that we took was basically a series of batch and column experiments, primarily using artificial systems in the lab. I will touch on a little bit of work we did with field collected material towards the end. And the batch experiments were primarily aimed to understand equilibrium conditions. So essentially, what would the equilibrium be between the solid phase and solution phase for these compounds, both with and without co-contaminants being present? And then we wanted to move into column experiments. These are one-dimensional column experiments to try and mimic advective conditions, systems that perhaps may not be at equilibrium. So we looked at these under unaltered conditions with and without co-contaminants, but then also when chemical oxidants might have been deployed, both with and without co-contaminants. And when I'm talking about co-contaminants, I'm primarily talking about non-aqueous phase liquids as the the worst case, if you will, of having co-contaminants present at many of these sites. So jumping right into some of the results that we observed, one of the most striking things from our initial studies were that the short chain compounds, as Jennifer has already talked about, the vast array of perfluorinated species, not to mention the polyfluorinated species at these sites, the perfluorinated species did not quite behave as we expected them to. They are transported, they do absorb less and thus would be transported more rapidly than some of the longer chain compounds, but they're not transported, or they don't absorb as minimally as we would have originally expected. So I've circled here on the upper left the fact that the short chain compounds exhibited much stronger log KD values than we would have expected from the extrapolation from the longer chain length compounds. Generally speaking, the perfluorochemicals do strongly interact with organic carbon, so understanding the FOC of your material, or whether it's soil or sediment, is going to be important. But that tends to fall apart a little bit with these short chain compounds. So we're not fully understanding at the present what impacts these short chain compounds. So specifically the butanoic, pentanoic, and hexanoic acid. If we look at the KD versus FOC, in some cases you might say that is a relationship for PFBA, but certainly for the pentanoic and hexanoic acid, they don't seem to be as strongly dependent on the organic carbon content of the material. I'll note that the minimum absorption, thus the maximum transport potential, really does occur with the C5 and C6 compounds. And I've shown here the perfluorocarboxylates. The perfluorosulfonates are a little bit different, but we generally see that these shorter chain length compounds are transported more readily, but their behavior is a little bit different than we would have otherwise expected based on previous studies. Moving into our column studies, this was really an attempt to say if we have conditions where that may not be conducive to actually having equilibrium, do we see things like non-equilibrium transport in column systems? And the short answer is for the longer chain length compounds such as PFAS, yes, there is certainly evidence for rate limited or non-equilibrium transport. So on the left here is shown what we would have expected for equilibrium transport in terms of breakthrough, and the fact that the actual data from the column shows early breakthrough, at least for PFAS in the system, suggests that non-equilibrium transport is occurring. PFAS is not coming into equilibrium with the solid phase. I'll mention that these results are from conditions that represented very high flow. And when you have a low flow groundwater or low linear velocity in terms of the groundwater, you very well might have equilibrium conditions. But when you have very high flows, certainly the potential for non-equilibrium transport of some of these more strongly absorbing compounds is there. And that is verified with the figure on the right, where we see when we have transport through a column and we stop the flow, as indicated there, that if you have non-equilibrium transport or rate limited absorption, when you stop the flow, you allow the system to come to equilibrium, and if it's not at equilibrium, you would expect a drop in concentration. We actually observe that in our columns, providing further evidence that non-equilibrium transport or rate limited absorption can be important for some of these compounds, particularly PFAS in these systems. Now moving on to the presence of co-contaminants, we did a number of studies both in column and in batch systems to look at the co-contaminants being present, and what I'm showing here is primarily focusing on the NAPL, so the non-aqueous phase liquids. And on the left are shown two isotherms for two compounds, the butanoic acid, the short chain carboxylate, and the perfluorooctane sulfonate, PFAS, the long chain sulfonate, and isotherms with and without the presence of TCE NAPL. And so we evaluated both TCE as a model chlorinated solvent NAPL as well as dodecane as a model fuel NAPL. And as you'll see in a moment, there's not a huge difference between those two, but the truth is that these compounds do interact with NAPLs when they are present. Generally, we see a greater impact in terms of the absorption potential for these compounds when there's low organic carbon in the material in the solid phase. So a very sandy material might have a much more impact of having an NAPL present than a very high organic carbon material. And we generally saw more of an impact for the shorter chain length compounds. And in fact, in some cases, we actually did observe slight decreases in absorption potential for the longer chain length perfluoroalkyl acids. Excuse me, I'm getting over a cold a little bit. And the other thing that we observed was that when we had NAPL present, we generally observed much more linear isotherms for these compounds in these systems. So that suggests that perhaps there was some absorption into the NAPL. And I'll touch on that in the next slide. We certainly think that is possible. That's probably not the only mechanism by which these compounds are interacting with the NAPL. And the fact that we saw variable effects on the NAPL for the short chain versus long chain, I think just speaks to the complexity of these types of interactions. And that's further illustrated in this next slide, where I'm reporting the K-NAPL values measured from batch systems for a variety of compounds, both using the dodecane, the KDD being a dodecane NAPL here, as well as our TCE NAPL. And I've circled specifically the cases where we have PFOA and PFAS, just because those are of generally most interest for most of this community. But certainly we measured the absorption to the NAPL of a lot of these other compounds. What was interesting was that when we took if you assumed that there was absorption into the NAPL, so true partitioning into the NAPL phase, and you combine that with what you knew about the absorption onto the solid phase into a linear model, so assuming that simple absorption into the NAPL and absorption onto the solid phase was driving the absorption in the system where we have the soil, the NAPL, and the water. When we compare that to what we actually measured, we saw that our predictions underpredicted when NAPL increased the absorption of these compounds. We underpredicted the amount of absorption as compared to what we actually measured. And what we think is probably happening here is that it's not just absorption into the NAPL, but it's likely also adsorbing onto the NAPL water interface. And that's something that we were trying to explore a little bit further, but certainly in batch systems we see evidence that these fluorochemicals will interact with NAPL, and it's not a pure NAPL water partitioning type of interaction. So the next round of experiments I'm going to discuss are a little bit more complicated. And what we were trying to do here, we were trying to mimic the transport and the effects of applying chemical oxidants in these systems, and how these fluorochemicals would be affected when these chemical oxidants are added. And so what are showing here is a number of experiments, or the kind of experimental setup where we have a number of pore volumes of groundwater flowing through the system. And we had perfluoroalkyl acids added in the groundwater, and then we took them out and we added them again over here. But then also when we had the fluorochemicals in the system, we added a chemical oxidant, one pore volume of that chemical oxidant, and then a longer extended oxidation phase shown here. And then the oxidants that we were looking at were persulfate, permanganate, and catalyzed hydrogen peroxide. And these experiments were done both in the presence and absence of TCE as our model NAPL. And you can see the residual saturations were relatively high. And what we're observing here is what we kind of expected as a hypothetical breakthrough curve, where we have initial breakthrough of the compounds, perhaps an effect of the pulse of chemical oxidants, maybe more of an effect when we had a longer term application of the chemical oxidants. And then we have our desorption phase. And this second breakthrough curve over here is meant to understand to what extent the chemical oxidants have altered the absorptive behavior of the geomedia for these perfluoroalkyl acids. So that's the general setup and how we conducted these experiments. Now this gives you a flavor of some of the results. And essentially when we have, and this is a case showing when we don't have any NAPL present, so these are all without the presence of any co-contaminants, what we observe is that permanganate and catalyzed hydrogen peroxide are two chemical oxidants that seem to show minimal effects. So the green boxes kind of indicate our qualitative scoring of whether or not we are observing a major effect of those chemical oxidants on the breakthrough of the various compounds shown here in the table. And those are illustrated in the figure on the left here, where we see PFBA, for example, and permanganate is basically not affected at all by the addition of the chemical oxidants. So the green is indicating basically no effect. The light blue is indicating the fact that we see perhaps a small dip, as illustrated here, for PFOA and catalyzed hydrogen peroxide upon the addition of chemical oxidant. And the orange is indicating, the purple first is when we have an effect, a very large effect, a very large dip in the concentration in the effluent coming off the column when we add the chemical oxidant, but it does eventually recover, versus the orange when we have a large dip and it doesn't really recover over the course of the experiment. And as you can tell from the table, permanganate and catalyzed hydrogen peroxide really had very little effect in terms of the retardation of these compounds in the system. But persulfate did have a major effect. Essentially, we saw a pretty substantial enhanced retardation when persulfate was added to the system. And this was more pronounced for the longer chain length compounds. So the longer chain length compounds were generally more affected by the chemical oxidants, and this was more so the case when we added persulfate. And I know that there will be a question, was this actual enhanced retardation? And I won't show you the data here, but essentially we did do a mass balance on these systems, and unfortunately we recovered basically all of the mass in these systems, or could explain the mass in all of these systems. So we were pretty confident that the effect was not that we were degrading any of these compounds with these chemical oxidants, but rather we were impeding their transport through the system. So one other way of looking at this was to look at the initial breakthrough of the compounds on that initial breakthrough part of the curve as compared to the breakthrough after the oxidants had been added. So the green shown here in this prototypical, if you will, experiment or profile versus what we would observe after the chemical oxidants have gone through the system. And when we do our breakthrough experiments, we calculate and fit our data with our retardation values, and we compare the pre versus post retardation factors. Essentially, we observe that persulfate generally increases the retardation factors for these compounds, whereas the other chemical oxidants will decrease the retardation factors for these compounds. And again, I don't have time to go into the details of this, but we believe that at least in the case of persulfate, this is mainly driven by the very large drop in pH in these systems. Essentially, we drop a pH to close to 2 when we add the persulfate to the system, and it takes a very, very long time for that pH to come back up. And so we think that that drop in pH is one of the major factors by which we see greater retardation of these compounds in the presence of persulfate oxidation in the system. And we'll have other explanations as to why we see less retardation for the other chemical oxidants, mainly through the potential degradation of the absorptive sites via the degradation of the organic matter in the system. We also looked at the desorption behavior. As we indicated, there are some cases where there's potential for rate-limited absorption, so we wanted to understand how do these compounds desorb from the system as well. And so we looked at the breakthrough, or sorry, the tailing of the initial breakthrough curve over here, right after the oxidant had been added essentially, and then in the second pulse over here of the fluorochemicals, fairly long time after the oxidants had been added. In these cases, comparing these two desorption curves, we still see that persulfate slows down the process. So persulfate, we saw much slower desorption of these compounds looking at this first phase as compared to the case where no oxidants had been added. And then again, in the second phase, we saw much slower desorption when persulfate had been added to the system. Interestingly, for the other chemical oxidants, we saw minimal to no impact after that first round of oxidation. But over time, we saw that the fluorochemicals desorbed much more rapidly from the systems that had been exposed to these oxidants, again implying that the chemical oxidants do have an effect beyond just the change in the solution chemistry. They might actually change the content of the solid phase and thereby affect the absorptive potential of that material for these compounds. And just to emphasize that one last time, we did do some column experiments, at the end of the column experiments, we did dissect the columns essentially and take out samples, measure the organic carbon. We did see in some cases some organic carbon had been destroyed by the chemical oxidants, as one might expect. And we also measured in situ KOC values, and we saw that when we had persulfate added to the system, we generally saw an increase in the log KOC values for a lot of these compounds. Very little impact of the catalyzed hydrogen peroxide, and for the permanganate, we tended to see a slight decrease in the log KOC values. And this plot here is showing the average delta log KOC for these compounds for all these different perfluoroalkyl acids. So how does this all fit in? If we go back to our site and we look at the plumes that had been measured, we can now actually, and we did actually make some predictions using a HYDROS 2D of what you could potentially expect in terms of the relative transport of the hexanoic acid, for example, as compared to the octanoic acid. And this is just the fact that we did not see the differential transport as we would have expected from our laboratory experiments in the field is one line of evidence, along with a lot of other lines, that led us to conclude that we were probably seeing, at least in the field, some ongoing release of perfluoroalkyl acids from these source zones. And I think Jennifer has alluded to the fact that these precursors are certainly likely present and potentially being transformed to these perfluoroalkyl acids and then released. And our follow-on work has attempted to look at that just a little bit. And so this is where we were able to obtain materials from a source zone. And so these were real field collected materials, and we basically put them in a column and leached them with artificial groundwater. And we see for the hexanoic acid, we see fairly rapid release of hexanoic acid from the system. Octanoic acid is a little bit slower. PFAS is even more slow. But if you look up here on our legend, we did these in the case of having no oxygen in the system, but we also added chemical oxidants, in this case permanganate and persulfate. And what was particularly interesting, if we come down here, if we do the mass balance on what came off of those materials over the course of these leaching experiments, in the case of permanganate and the perfluorohexanoic acid, we actually observed 10 times the mass of hexanoic acid coming off the soil as we had initially measured on the soil to begin with. And this again is a very strong line of evidence to indicate that we have precursors present in these soils, and those precursors are being oxidatively transformed by that permanganate to these hexanoic acid compounds, which are then being leached off the soil. So again, this really does speak to the importance of understanding the source zones in these systems. So just to wrap up, our study really focused on transport of these compounds, and we do believe that the transport of these compounds, the perfluoroalkyl acids, is going to be dependent on the perfluorocarbon chain length, but not necessarily as linearly as when we had initially started. We see the short chain compounds do absorb a little bit more strongly than we had initially anticipated. We do see interactions of these compounds with NAPL. We think it's both an ad as well as an absorption process, and so it's actually quite complex. But we see that those interactions are likely occurring. We see that chemical oxidation does affect the transport of these compounds, primarily through alterations in both the solution and solid phase geochemistry, with persulfate being the strongest impact on the transport, we believe primarily through the large drop in pH that we observe. And I think all of this research, particularly some of the later results I showed here, strongly emphasize the need for source zone characterization, as Jennifer has already alluded to. With that, I'll just mention a number of ongoing projects. One of them Jennifer has mentioned, some additional source zone and characterization, and of course I'll be happy to take any questions if folks have them.
Great, thank you, Chris. We only have time for one or two brief questions. A question from the state of California. The firefighting training site I'm working on has DNAPL. How do PFOA and PFAS behave in the presence of chlorinated VOC?
Well, I'll mention that the experiments that we've primarily focused on were for TCE NAPL, and so I think that those could be certainly indicative of the sorts of behavior you would observe at that field site. Now, we haven't done experiments with all the different NAPLs, but I think the fact that we have similar behavior between our dodecane and our TCE suggests that if you have some sort of non-aqueous phase liquid present, you're likely going to have some sort of interaction between these compounds and that NAPL phase.
Great. And one additional question from US EPA. Where petroleum chlorinated compounds were present at sites or where AFFF was used, have you observed dioxin generation in your samples following the burning of these fuels at these sites?
I will have to default to someone else there because I have not actually done a lot of field characterization and certainly have not looked for any of those other contaminants. And what I'm presenting here is primarily the work we've done in the laboratory, and we certainly haven't observed that, but neither have we really looked for those sorts of things in our laboratory experiments.
Thank you, Chris. Maybe Jennifer, do you have? Can you weigh in on this question?
I don't have an answer, but I want to acknowledge the importance of the question, that these sites were sites where incomplete combustion took place. And so it's a pertinent question. I just don't think those of us in the PFAS game know the answer to that, but we applaud the question.
So I'm hearing a lot of unknowns. So when each of you, and by you I mean our three speakers, when each of you looks at the current knowledge on PFAS, how far along are we truly away before having the knowledge needed to fully address the environmental PFAS issue? So maybe we can start with you, Dr. TerMaath.
Could you repeat that about you said the PFAS? I'm sorry.
Yes. When each of you looks at the current knowledge on PFAS, how far along are we in having the knowledge we need to fully address the environmental PFAS issues?
I think we're not very far along. I think that we'll be having to press on with trying to figure out the extent of contamination long before we find out some of the parameters that would be nice to know, because of the drivers for impact on drinking water and everything else. I think we're probably on about 20% of the way forward.
Thank you. Chris, can you please weigh in?
I think several of us are really trying to understand all the different chemistries, and I think we're getting towards the point where we can understand the types of complex interactions that occur. But unfortunately, it's not just one or two compounds. It's a suite of compounds, some of which we're only recently identifying. And the behavior is not simple, as indicated by the NAPL data. I mentioned the NAPL interactions, but we have no idea to what extent some of these polyfluoroalkyl species interact with those sorts of phases as well. So 20% assessment, perhaps that's a good one. I actually have no real sense of how far we have to go, because it keeps getting more complex.
Thank you. Jennifer, can you please weigh in?
Well, I'm going to put a slightly more positive spin on it. If we think of the broad categories where we need information: characterization, biodegradation, transport, and last but not least, toxicity. If I think of it as a little like a racetrack and each horse is moving at different speeds, I would say that because of the SERDP program, the characterization question, what's out there, what's the species, how do we measure those, that's pretty far advanced. And in fact, we hope that we put most of that behind us here fairly quickly. But then when we turn our attention to biodegradation, there's some really big gaps left out there. For example, we really have no information on the biodegradation pathway of the 3M chemistries. We know a lot more about the Ansel. We know less about 3M and nothing about National Foam. So that horse hasn't moved that far out of the barn. Transport, Dr. Hayden has been working on this for quite some time and is really pushing that forward. We hope to contribute in the new chemistries. That's moving along. There's still quite a ways to go. And of course, the problem with tox is, we've known about these substances in military groundwater dating back to the 90s. And knowing that they're out there, what you see is the tox. A lot of the tox information came along behind that. And so tox tends to lag significantly behind. It's not unique to PFAS, but I think it's true for a lot of different emerging contaminants. It lags significantly behind the discovery and the characterization. So that one, and again, it depends on if you're looking at human or ecotox. Those individual horses in that lane are moving at different rates. So some things we've got a pretty good leg up on. We have the tools now, and now what we need is the focus and, of course, the resources to really drill down on the biodeg, the transport, and the toxicity.
Thank you, Jennifer, and I'd like to thank actually all our speakers today for a very informative webinar. For our audience, I'd like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. Our next webinar is on Thursday, February 11, and it will feature two presentations highlighting Department of Defense efforts to replace chromate and other hazardous materials in coating systems for military aircraft and ground support equipment. We will have three speakers, Julia Russell and Brenna Lynn Skelly from the Naval Air Systems Command, and also Mr. Michael Spicer from the U.S. Air Force Coatings Technology and Integration Office. Registration is open for this webinar, so please visit the SERDP and ESTCP webinar webpage to register for this free event. And before I let you all go, we would really appreciate it if you can please take a moment of your busy day to complete the survey that will pop up on your screen at this time. This concludes today's webcast. Thank you all for your time.